Welcome to this lecture module on optics. In the last class, we discussed about refraction by spherical surfaces and then by lenses. We also derived the lens formula and we have seen expression for the magnification. We have also seen formation of image by a lens. So, let me quickly recap what we have studied before we take up today's topic, and today's topic is power of a lens and combination of thin lenses in contact. So, before we take up this topic, we will just quickly recall what we had studied in the last lecture, and I will take a couple of examples. So, refraction and image formation by lenses. So, this is the summary of what we have studied. So, we have derived the thin lens formula. There is a lens here, a biconvex lens, an object of height h forming an image of height h dash. F1 and F2 are the principal foci of this lens. U is the object distance, V is the image distance, and F is the focal length. R1 is the radius of curvature of the first surface, R2 is the radius of curvature of the second surface, N1 is the refractive index outside the lens, and N2 is the refractive index of the material of the lens. And we have derived the lens formula, thin lens formula, 1 by V minus 1 by U is equal to 1 by F, with 1 by F is equal to this expression, where all the parameters are shown in the figure, and the magnification, lateral magnification, is equal to h dash by h, size of the image by size of the object is equal to V by U. We have seen that for a converging lens F, the focal length is greater than 0, focal length is positive, and for a diverging lens, focal length is less than 0, that is, focal length is negative. So, we come back to some examples. We will try to work out a couple of examples here. So, exercise. A 2 centimeter long needle is placed erect at a distance of 10 centimeter in front of a thin biconcave lens. So, what is given is a thin biconcave lens. Distance is 10 centimeter. Height is 2 centimeter. It is a 2 centimeter long needle placed erect, which means it is sitting straight. And the focal length of the lens is given as 10 centimeter. Determine the position and size of the image. To draw a ray diagram with appropriate numbers for the object distance, image distance, etc., showing formation of the image. So, let us first look at the first part. We have to be careful, it is a biconcave lens. What we quickly observe is that the object distance U is the same as focal length 10 centimeter, both are same. So, we may jump to a conclusion that in the case of a biconvex lens, if the object is placed at the focus, then the image is formed at infinity. But this is a biconcave lens. Here we are dealing with a biconcave lens, and therefore, let us see what we get. So, let us use the thin film thin lens formula. So, the thin lens formula. So, 1 over V minus 1 over U is equal to 1 over F, or let me take 1 over U to the other side. So, plus 1 over U. So, given its U is equal to, it is 10 centimeter in front, 10 centimeter in front. So, U is equal to minus 10 centimeter. It is a biconcave lens of focal length 10, therefore, F is also equal to minus 10 centimeter. F is equal to, is a biconcave, therefore, F is equal to minus 10 centimeter. Therefore, 1 by V is equal to minus 1 by 10 minus 1 by 10, which is equal to 10 centimeter each. So, minus is common. So, we have 2 by 10, which is equal to minus 1 by 5, or V is equal to minus 5 centimeter. V is equal to minus 5 centimeter. Therefore, immediately, so we need to find out the position. So, position is where the image position is minus 5, which means in front of the lens, and what we also have is the size. So, size is given by m is equal to V by u, which is equal to minus 5 centimeter by minus 10 centimeter, which is equal to 0.5, and therefore, this is equal to size of the image divided by size of the object. Therefore, size of the image is equal to 0.5 into size of the object. Object size is given 2 centimeter long needle, therefore, is equal to 2 centimeter, which is equal to 1 centimeter. Note that the size is 1 centimeter, which means it is an erect image. It is a virtual image because there is no negative sign. It is not an inverted image, it is an erect image, and the image is formed at minus 5 centimeter in front of the concave lens, biconcave lens. So, let us try to, with these two data there, let us try to draw the diagram here. So, here we have, so let me show here itself. Here we have a biconcave lens. The axis is shown here, this is the axis, and here is the object. So, this is the focal length and also the object distance. So, this is minus 10 centimeter, this distance. So, we consider image formation. We have to draw a diagram showing image formation. So, we consider a parallel ray and a ray passing through the axis like this. The parallel ray will get deflected because it is a biconcave lens. The focal length is here. So, this is also the focal length f, and therefore, it would go in such a way that it will appear to come from the focus. That means, the ray would travel like this. It would appear to come like this. The ray which is going through the geometric center of the lens will go undeviated. Therefore, the intersection point here is where the image is formed. So, the image is formed here. So, this is the object of length 2 centimeter and image is formed here. So, what we have got is this position, the image position is 5 centimeter. This is minus 5 centimeter. Minus sign because we are on the left side of this. Rays are coming from the left side and the distances to the left of the lens are negative and distances to the right of the lens are positive. This is what we see now is this is 1 centimeter height, this is minus 5 centimeter. This is almost obvious if you see the geometry carefully that this is a triangle where this is 2 centimeter, a parallel ray comes here, therefore, this is also height 2 centimeter, this is 10 centimeter, and therefore, the rays, the diagonal, these are the two diagonals which will intersect at half the point, that half the distance, which is minus 5 centimeter, and the height will also be equal to half the object height. That is what we have got from the mathematics, which is consistent with the geometry. It is a very simple example, but also tells you how to record formation of the image. So, this is consistent and a simple example. So, let us take a second example. So, let me look at a second example. So, exercise 2. A particular lens made of glass of refractive index 1.5 has a focal length f in air, that is n equal to 1. When the lens is immersed in a liquid, the focal length increases to 4f. So, this is 4f. Here it is f. Refractive index is given 1.5 and outside it is air, and when it is immersed in a liquid, focal length increases to 4f. Determine the refractive index of the liquid. So, the given data is, we have a lens of material n is equal to 1.5. When the outside medium it is air, then we have a certain focal length. So, if I show quickly the focal length like this, so this distance is f. What is given is, if this lens is immersed in a liquid, the focal length will increase to 4f. So, when it is immersed in a liquid, so let me use a different color, the focal length increases to 4f. So, it is intersecting somewhere here, and this separation is 4 times the original separation. Determine the refractive index of the liquid. So, how do we go about this? So, let us use the lens formula, and we know that the focal length 1 over f is given by n2 by n1 minus 1 into 1 over r1 minus 1 over r2. This is the formula for the focal length. N2 is the refractive index of the lens, and N1 is the outside medium. So, when this is, so for the particular case, the problem, it is f when it is n glass. So, let me write this as n glass, Ng standing for n glass, divided by n air. So, Na is refractive index of air, minus 1 divided by multiplied by 1 over r1 minus 1 over r2. And this is first data, and it is 1 divided by 4f. The focal length has increased to 4f when we have, instead of air, we have the liquid. So, we have Ng, refractive index of the lens, material of the lens remains the same, but now we have NL. NL is that of the liquid. So, we are asked to find out what is this NL, minus 1 into the same terms 1 over R1 minus 1 over R2. Here. So, very simple, we simply divide. If I call this as equation 1 and equation 2, if we divide 1 by 2, then we have here f cancelling, and we have 4 going upward. So, we have 4 is equal to, these terms cancel, this bracket completely cancels with this. This I can write as Ng minus Na by Na. So, I have Ng minus Na by Na divided by Ng minus NL by NL, but it is in the denominator. So, I have to flip it. So, NL divided by Ng minus NL. That is it. Now, we can substitute the values of the refractive index. Ng is given as 1.5, this is 1. So, 1.5, which is equal to, let me substitute, 1.5 minus 1 divided by 1. So, it is simply 0.5 by 1, which is 0.5 into NL divided by Ng minus NL. So, this is 0.5. So, 0.5 goes to the denominator, this will become 8. 8 is equal to Ng, that is 1.5, sorry, NL, sorry, 8 is equal to NL divided by Ng is 1.5. So, 1.5 minus NL. So, we can transpose, and let me continue here in this line. So, if I take this here, we have 8 into 1.5 minus NL is equal to NL. So 8 NL goes to the other side, can become 9 NL. 8 into 1.5 is 12. So we have 9 NL is equal to 12. 1.5 into 8, or NL is equal to 12 by 9, which is equal to 4 by 3, which is equal to 1.33. 1.33. The refractive index of the liquid is 1.33. This is the refractive index of water. We are familiar that refractive index of water is 1.33. And we see that if you have a lens which is in air of certain focal length f, and if you immerse the lens in a liquid of refractive index NL, then if you immerse it in water, then the focal length becomes 4 times f. All right. So these two simple examples I had taken to illustrate the applicability of the formulae which we have derived. And now let us proceed to the topic of power of a lens. What is power of a lens? So power of a lens. The converging or diverging capability. So the converging or diverging capability of a lens is quantified by the parameter power of a lens. What does a lens do? A lens can either converge or diverge a parallel beam. A parallel beam incident on a convex lens will converge to the principal focus. And if it is incident on a concave lens, for example, if it is incident on a concave lens, then it will diverge. So converging or diverging capability of a lens is quantified by power of a lens. Intuitively, what I have shown in this diagram here is the green colored rays here focus to a point F here. It's a thinner lens with a larger focal length. Then it is converging slowly or weakly converging. The focusing ability, the focusing is slowly happening here to this point. Slow in the sense with distance, not in time, with the distance. Whereas in this case, it is focusing rapidly to a point F which is close to the lens, and therefore smaller the focal length, stronger converging ability, and larger the focal length, weaker converging ability. In other words, intuitively we can say that the converging capability is inversely proportional to the focal length. So the power of a lens is inversely proportional to the focal length. The same thing what I have shown is with respect to a convex lens, but the same thing will be true if I use a concave lens. So if you have a concave lens like this, a concave lens which has a larger focal length here, which means parallel rays which are incident here will appear to diverge from this point. So if I show this as the focal point or focus, then it appears to diverge in this direction, and similarly it appears to diverge along this line. Whereas if the focus were here, then the ray would have diverged like this. So the diverging capability, whether it is converging, so the ray would have gone like this. So the diverging capability or the converging capability, as we saw in the earlier case, depends on the focal length. Small focal length, stronger divergence, and in the biconvex case, small focal length, that means it is a stronger convergence, and here it is a stronger divergence. In either case, the converging power or diverging power are inversely proportional to the focal length, and therefore the power of a lens is defined as the power of a lens P is defined as P is equal to 1 by F, where F is in meters. It is very important to recognize that the focal length has to be substituted in meters. So the unit is meter inverse, which is in this case is also called diopter and denoted by the symbol capital D. Thus, for example, a convex lens of focal length 50 centimeter has power P is equal to 1 divided by 0.5 meters, 50 centimeter, which is 0.5 meters, and which is equal to 2 diopters, 2D, D standing for diopter. Similarly, if we use a concave lens of focal length, let us say 40 centimeter, then the power P is equal to 1 divided by minus 0.4, because it is given that it is a concave lens. So, the focal length is minus 40 centimeters, which is minus 0.4 meters, which is equal to minus 2.5 D. Normally, conventionally, when we talk, we drop this D and we say that the power is plus 2 or power is minus 2. This is what people refer to particularly with regard to spectacles, the power of spectacles. Someone says that I am wearing a spectacle of power plus 2. So, a power plus 2, what does that mean? So, my spectacle lens has a power P is equal to plus 2. What he implies is this means it is plus 2D, and this implies that the focal length is equal to 50 centimeter, 50 centimeter, and focal length it is plus, therefore, focal length is positive, which implies it is a convex lens, convex lens. The lens used in his or her spectacle is a convex lens of focal length 50 centimeter. Similarly, if one says power is equal to minus 1, this is commonly when we talk, we say power is plus 1, minus 1 and so on. We normally do not use D, but it implies the power is minus 1D, which implies the focal length F is minus 100 centimeter or 1 meter, which implies it is a concave lens. Concave lens. Why some people use convex lens and why some people use concave lens is convex lens and concave lens depends on the defect in the vision that they have. This we will discuss at a later time. All right. So, it's very important to remember that F has to be substituted in meters when we calculate the power. Right. So, let us now move on to the next topic, which is combination of thin lenses in contact. Combination of thin lenses. Consider two thin lenses L1 and L2 here, L1 and L2 of focal lengths F1 and F2 placed in contact. So, first the focal length, a thin lens L1. I have shown in this case both as convex, biconvex lenses, but it could be one biconvex, one biconcave, or one plano-convex, and etc. But consider two lenses L1 and L2 of focal length F1 and F2 placed in contact. They are in contact here. They are just touching each other without any air gap at the center here. There will be some air gap at the ends, but they are just touching each other. So, what would be the focal length of this combination? If this has a focal length F, what would be F? That is how F is related to F1 and F2. So, this is what we have to determine. Now, there are other combinations possible. In this case, I have shown that it is converging because intuitively I know that the first lens is converging, the second lens is also converging, therefore, the combination must be converging. But in a general case, when you have one convex lens, one concave lens, for example, then it is not possible to straight away say whether the combination will act as a converging lens or a diverging lens is not clear. So, we have to have a method of seeing that. As I said, there are other combinations which are possible. For example, we may have a convex lens like this and a concave lens which is also just in contact. So, here is the concave lens. So, L1 is, so F1 is greater than 0, but F2 of this lens, F2 is less than 0. What about the combination? It will depend obviously on the values of F1 and F2, as we will see. In some cases, we have plano-convex lens. So, in one side it is plane, another side it is convex, and we may have a concave lens, plano-concave lens. So, like this. In this case, F1 is greater than 0 again, and F2 is less than 0. Now, why do we use such lenses? There may be more lenses. So, why go for combination of lenses? Combination of lenses. Why use combination of lenses? There are several reasons. One of the reasons we will see that you have a lens of focal length f1 and a lens of focal length f2. It could be both convex or both concave or one convex, one concave. Then it is possible. So, one of the reasons is it is possible to obtain an f which is required for a particular application. Required for a particular application. This is one of the reasons, particular application. That is, we have lenses of focal length f1 and f2, but we do not have a focal length of lens, a lens of focal length f. Then it may be possible sometimes to have a combination, so that we can have a combination which has a focal length f that is required for a particular application. But this is not the main reason. There are other reasons. Usually, one of the lens will be of a particular material of refractive index n1, then the other material of the second lens is usually different, and this is for. So, if we have one, so let me show in the same diagram here. This could be of refractive index n1 and this could be of refractive index n2. One of the important applications is what is called to compensate for chromatic dispersion. Chromatic dispersion. We will discuss about dispersion in one of the subsequent classes. So, chromatic dispersion, compensate for chromatic dispersion. Every material has a certain dispersion. N1, this material has a certain dispersion, this material has a certain dispersion. Dispersion refers to refractive index seen by different wavelengths of light. Different wavelengths of light will see different refractive indices. This is called dispersion or chromatic dispersion. The effects of chromatic dispersion we will discuss a little later, but compensation means the dispersion due to one lens can be compensated by dispersion due to another lens if the materials are different, so that for all wavelengths the behavior of the lens is the same. We will discuss this at a later stage, but this is the major application of using a combination of multiple lenses. Okay, so let us come back to the problem. So, how to determine the focal length of this combination? Now, we should recall that in determining the lens formula, what we did was, this was a lens with the two refracting surfaces, R1 and R2. So, this is refracting surface R1 and this is refracting surface 2 of radius of curvature R2. So, we treated first this as one surface R1 followed by refraction at the second surface. Refraction at the first surface, this is just to recall, because we want to apply the same technique here. Recall that refraction by a lens here. So there was an object and rays travel and formed an image I. So this is a point object, an image I. This was treated as first refraction by the first surface here, followed by, so this would form an image somewhere here, let us say I1, and this image will be treated as a virtual object for the second image formation. So this, the ray which is coming from here will, so let me draw this, we have already discussed this in detail. So forms an image here. So this is I. So we first applied the formula for this refraction and then treated this refraction, where we have, so this is I1 and this was the virtual object for the second refraction. So this is the image distance, this is the actual object distance, actual image distance, which is treated as first the actual object distance, object here, which forms an image in the absence of the second refracting surface, and then the second refraction at the second surface considers I1 as the virtual object and forms an image at I, and then we derived the lens formula. So we got the lens formula by, so lens formula, we derived the lens formula by successive application. So successive application, that is one after another, successive application of the formula for refraction at a single interface. So successive application of the formula for single interface, we did this to obtain the lens formula. We follow the same procedure now. So here, so that the picture will become clear when I place this. Now let us look at this. So here it is. So let me cover the rest. First, successive application of the thin lens formula. There are two lenses. So first we treat this first lens, refraction at the first lens and second lens. Earlier we treated refraction at the first interface and the second interface. Now first lens and second lens. Now because we are treating thin lenses, since the lenses are thin, we assume the optical centers to coincide midway between the two lenses. So here it is, the optical center here of the first lens and the second lens is assumed to coincide at the midway, because it's thin lens, so the difference is very small. So we assume that to be the center, so that this is the object distance and this is the image distance, the combination forming object distance, image distance. Object is here and image is here. Now first, for the image formed by L1, so let us look at this. We first consider image formed by the first lens. The object is here minus u, and the image is formed here in the absence of the second lens. When the second lens is not present, the first lens would have formed an image at the point I1 and at an image distance which is V1. And we know the thin lens formula, 1 by V1 minus 1 by u, this is the object distance, is equal to 1 by f1, where f1 is the focal length of the first lens. Now we apply refraction by the second lens. So here it is, the second lens. For the second lens, I1 acts as the virtual object, because the object ray is coming from here. This is the object ray which is coming. So the object ray is coming from here, which would refract to form the actual image here. The object ray would have come if the virtual image, the image which is here, is treated as a virtual object. That is, if a ray were to start from here, it would have gone along this ray. along this ray, which is the object ray, and that's why it is called a virtual object. So the object ray undergoes refraction and forms the image here. So for this, the thin lens formula tells us that 1 by V, this is the image distance, minus 1 by V1, V1 is the object distance, now virtual object, is equal to 1 by F2, equation 1 and 2. Successive application of the thin lens formula, successively for the first lens and the second lens. If we set up, once we set up these two equations, I1 is the virtual object for L2. Once we set up these two equations, the rest is very simple. The combination of thin lenses, adding equations 1 and 2, so the same equations 1 and 2 we can add, we can see that this cancels, 1 by F1 plus 1 by F2 on the right hand side, this cancels and we are left with 1 by V minus 1 by U. So that's what is written, 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2, which is equal to 1 by F. That is, with 1 by F is equal to 1 by F1 plus 1 by F2, we can write 1 by V minus 1 by U is equal to 1 by F. This is of the same form as the thin lens formula for a lens of focal length F. This implies the combination behaves like an equivalent lens of focal length F, So what does this mean? So 1 by F is equal to 1 by F1 plus 1 by F2. So the same form as that of a thin lens. Since 1 by F is the power P, power of the lens, this implies P is equal to, P is the power of the combination is equal to P1 plus P2, power of the first lens plus power of the second lens. So P1 is 1 by F1, P2 is 1 by F2. Now, so the power is added here, there is the sum of the powers of the two lenses. There can be several lenses, we can have combination of several lenses. We have seen two lenses, I had taken both as convex lenses, but as I indicated earlier, some lenses could be convex and some lenses could be concave, and that's what I have shown here, combination of several lenses. I have here again considered only 4 lenses, there could be more, but 4 lenses I have considered. As you can see, the first one is a plano-convex, second one is a biconvex, the dotted line indicates the material, lens material, dotted dots indicate the lens material. So this is a plano-convex lens, plane and convex, double convex, that is biconvex lens. Next one, that is L3, is a biconcave lens, and L4 is a plano-convex lens. One surface is plane, one is this. So again, the combination, so what is shown here as the shaded region is basically fixtures which hold the lenses together. So the equivalent, the combination as an equivalent focal length is equal to 1 over F1 plus 1 over F2 plus 1 over F3. So 1 by F equivalent is given by this. In other words, in terms of power, the equivalent power of this combination is the sum P1, P2, P3, P4. But note that some of them are concave and some of them are convex, which means some of the powers are negative, and therefore it is an algebraic sum of the powers of individual lenses. So the power of a combination of lenses is equal to the algebraic sum of the power of individual lenses. Now, the examples, let us work out some examples and understand this better. So here it is. So let me take a first example here. So here it is. What is the focal length of the combination of two thin lenses? A convex lens of focal length 30 centimeter and a concave lens of focal length 20 centimeter. Is the combination converging type or diverging type? The combination. So, this is an exercise from the textbook. It is a very simple exercise, but let us start with this. So, here it is. There is a lens, convex lens of focal length 30 centimeter and a concave lens of focal length 20 centimeter, but f2 is therefore minus 20 centimeter. We will see later on, does it matter if we interchange the position of L1 and L2. So, let us work out the focal length of the combination. So, what we know is 1 over f. So, let me keep this here and start working out like this. So, 1 over f is equal to 1 over f1 plus 1 over f2, which is equal to 1 divided by 30 centimeter, the first one, plus 1 divided by minus 20. So, minus 20 centimeter. So, that is 1 by 30 minus 1 by, so 1 by 30 minus 1 by 20, which is equal to, so 60 could be the common denominator. So, we have 60 and therefore, this is 2 minus 3, which is equal to minus 1 by 60. This is the focal length of the equal, which implies f is equal to minus 60 centimeter. What does this mean? This implies that the combination here acts as a, is a minus 60 centimeter. So, acts as a concave lens, of focal length 60 centimeter. So, the question is the combination converging type or diverging type? Because it is a concave lens. So, this implies it is a diverging type of lens. So, diverging type of lens. Whether we have L1 first or L2 first, does it matter? It does not matter, so long as the refractive index here and the refractive index here are the same. So long as the outside refractive indices are the same, it does not matter whether I place this one first and this one second or vice versa, because what we have used is simply summing. Whether I place this 1 by 30 later or 1 by 20 this side, it does not matter. Therefore, it does not matter so long as the refractive indices are the same on both sides of the combination. Okay. It is a very simple example, and now let me take up a second example. Let us take a second example. Consider a linear object of height 1.2 centimeter placed at a distance of 40 centimeter in front of a combination of two thin lenses in contact. I have shown here diagram that, so as shown in the figure. So, the figure shows L1 and L2, two lenses, convex and concave, and at 40 centimeter in front of this combination, an object, a linear object of height 1.2 centimeter is placed as shown in the figure. Given that the focal length of the convex lens is 20 centimeter and that of the concave lens is 10 centimeter, determine the position and size of the image. First. Second, draw qualitatively the corresponding ray diagram showing the formation of the image. So, to draw this, we have to know what are the position and size, that will help, and therefore, first let us determine the position and size of the image. So, how do we go about this? So, first we have to, it is a combination, therefore, we have 1 over f of the combination, which I can write 1 over fc of the combination is equal to 1 over f1 plus 1 over f2, and f1 is given So, this is 20 centimeter and the other one is 10 centimeter. So, this is plus, that is minus. So, this is 1 by 20 minus 1 by 10. So, that is equal to, so this is 1 by 20 minus 2 by 20 and therefore, this is minus 1 by 20. So, this is 2 by 20 and therefore, this is minus 1 by 20. This implies FC, that is the focal length of the combination, is minus 20 centimeter. Implies the combination acts like a concave lens. So, concave lens. This helps in drawing the image. So, concave lens. So, we have got the focal length. Now, once we know the focal length of the combination, we have to determine the position and size of the image, and therefore, let us go to determine the position and size of the. So, it is a concave lens. So, I am now representing it as a concave lens. I could as well keep it as a combination, but now I am representing it as a concave lens. And what is said is there is an object here at 40 centimeter from, so this is 40 centimeter. And we have a convex lens of focal length 20 centimeter, minus 20 centimeter. So, where will be the position of the object? So, we use the lens formula 1 over V minus 1 over U is equal to 1 over F. So, this is therefore 1 over V is equal to 1 over F. F is 20 centimeter minus 20 centimeter. So, minus 20 plus U. U is in front of the lens, therefore, this is minus 40 centimeter and therefore, plus 1 divided by minus 40. So, this is equal to, so this is 2 by 40 minus 2 by 40. So, minus is common. So, we have 2 by 40 plus 1 by 40. So, this is 3 by 40. So, minus 3 by 40. So, this implies V is equal to minus 40 by 3 centimeters. V is equal to. So, we have got V as minus 40 by 3 centimeters. So, once we have V, we proceed further. So, let me show here. V is minus 40 by 3 and therefore, the second thing to be noted is as shown here, we have to determine the position. So, we have got the position and then we need to determine the size of the image. So, we have V is equal to, so V is equal to M, the magnification is equal to H dash by H, size of the image by size of the object is equal to V by U. So, V is equal to minus 40 by 3 divided by U is minus 40 here. So, that is equal to simply 1/3. So, we have M is equal to 1/3 minus 40 by 3 divided by 40 by 3. So, this implies size of the image, is equal to 1/3 into. So, it is given that the object height is 1.2 centimeter here. So, 1/3 into 1.2 centimeter. So, that is equal to 0.4 centimeter. So, we have got the size of the image is equal to 0.4 centimeter. So, we have determined the position. The position of the image V is minus 40 by, so here we have determined the position of image V is minus 40 by 3 centimeter, which means it is on this side here, on this side, and we have got the size as 0.4 centimeter. So, original object is of 1.2 centimeter height, but the image is smaller somewhere here. So, now let us try to draw. So, now we can draw qualitatively the corresponding ray diagram showing the formation of the image. So, let us draw the ray diagram. So, let me try to draw it here itself now. So, here is the equivalent, either we show both the lenses or we say that this is the equivalent lens, the combination equivalent. This has a focal length, we have got the focal length of the combination, we have just calculated the focal length as minus 20 centimeters. So, this is minus 20 is the focal length f, and the object is at minus 40, double the distance. So, O is here, the object is here. So, this is minus 40, the object, the focus, and therefore, when the object forms, so let me show a parallel ray here, which will appear to go from the focus, because focus is minus 20, therefore, this would, if I draw, so this would travel in this direction. The parallel ray would go like this. Please remember that this is the combination of one convex and one concave lens. So, here the parallel ray appears to come from the focus. What about the second ray? So, the second ray we can pass from here, and therefore, let me pass from the center here. So, the second ray passes from the middle, and therefore, the point of intersection is here. This is the point of intersection. When you draw with a scale, so that it will be very clear, and this point here is minus image distance. Image distance is this distance from here to here. So, this is V. So, V, and V is equal to, this point is minus 40 by 3 centimeter. So, 40 by 3 is 13.33, that is actually equal to minus 13.33 centimeter. 13 point. Obviously, we can see that it is below 20, here is 0 and here is minus 10, minus 20. So, it is approximately minus 13.3, and we see that the size is smaller, original object is here and now the size is smaller. So, if we draw with a scale, we can clearly see that yes, our calculation is right, that we are getting a smaller object, demagnified image, a smaller image, demagnified image of size 0.4 centimeter, and at a distance, at an image distance V is equal to minus 13.33 centimeter. So, here is the image which is formed, and the magnification is 1 by 3, which is positive, which means we get an erect image here, erect image at this point. So, we have answered all the parts. We have determined the position of the image, size of the image, and finally, we have drawn the corresponding ray diagram. Draw it with a neat scale, but it will qualitatively look exactly like this, showing all the distances. Show the distance 40 centimeter, 20 centimeter, and V as minus 13.3 centimeter. Show this as 1.2 centimeter and this as 0.4 centimeter. That will complete the ray diagram. Okay. So, what I had considered is finally, now, okay, we can, it is a good idea to see what would happen if the lenses are separated. So, I will leave this as a question. So, what would happen? What if the lenses are separated by a distance of, they are not in contact anymore, a distance of 5 centimeter. The same principles have to be worked out. So, one could work out this, and I could give you the answer here. So, I have worked out, but so let me give the answer, that in this case the magnification m would come out to be 2.2 by 5. Earlier we got 1/3. So, this is the answer. Magnification would come out to be 1/3 and V, the position would come out to be minus 14 centimeters. We had got in our problem it was minus 13.33, minus 13.33. Now, it slightly changed. We got a magnification of 1 by 3, but with this you will get this one. So, I would encourage you to work this out and work out more problems to get a better feel.